Galaxy clusters are weighing more than the matter inside them physically allows. A galaxy cluster is the largest stable structure gravity has ever built. Hundreds, sometimes thousands of galaxies are held together inside a single gravitational well, drifting through a shared volume of space tens of millions of light years across. Between the galaxies, filling the empty regions almost completely, sits a thin, scorching plasma, gas so hot it glows in X-rays. This gas is not background. It is the dominant visible component of the cluster, outweighing every star in every galaxy combined. The behavior of this gas is one of the cleanest measurements in astrophysics. Hot gas trapped inside a gravitational well reaches a temperature set by the depth of that well. A deeper well requires faster moving particles to stay bound. Faster particles mean a higher temperature. Measure the temperature of the gas, and the total mass of the cluster falls out of the equation. The physics is well tested, the technique is decades old, and the math is not in dispute. Then the measurement is taken. The gas in a galaxy cluster is far too hot for the matter we can see. Across thousands of measured clusters, the gas is moving at speeds that imply a gravitational well several times deeper than every galaxy, every star, every wisp of glowing plasma could possibly produce. Add up every photon-emitting object in the cluster, and the total mass falls short of what the temperature demands, not by a fraction, by a factor of 5, sometimes more. The first instinct is to suspect the measurement. Temperature can be miscalibrated, distances can be wrong, instruments can drift, so the measurement was repeated on different clusters, with different telescopes, in different wavelengths, by different teams across different decades. The result did not move. The clusters are gravitationally bound by something that does not glow. Under standard physics, this should not be possible. A galaxy cluster is held together by gravity, and gravity is produced by mass. If the gas is hot enough to require a certain mass, that mass must exist somewhere inside the cluster. The visible matter is accounted for down to remarkable precision. Stars are counted, gas is mapped, dust is weighed. None of it is hidden. The shortfall is not a rounding error. It is the majority of the cluster. Yet the gas continues to behave as if the missing mass is present. It settles into the gravitational well it can feel. It reaches the temperature that well demands. It moves through a structure shaped by something the telescopes cannot find. The first attempt to close this gap was the simplest one. That the missing mass is ordinary matter, just hard to see. Cold gas, faint stars, planet-sized debris, dim remnants drifting between galaxies. Matter that exists, but does not glow brightly enough for current instruments to register. If enough of this dark, ordinary material were spread through the cluster, the temperature mismatch could resolve without invoking anything new. This explanation was taken seriously for a long time. Surveys were designed specifically to find it. Microlensing experiments scanned for faint stellar remnants. Deep infrared observations searched for cold gas pockets. X-ray observatories pushed to lower energies, hoping to catch matter too cool to have been seen before. The searches returned consistent results. The total amount of ordinary matter in the universe, including the parts that do not glow, is constrained by separate, independent measurements of the early universe. That budget is known. It is not enough. Even if every faint remnant and every cold pocket were included in full, the gas temperature in clusters would still demand more mass than ordinary matter, in any form, can supply. The shortfall is not hidden matter we have failed to see. It is matter that does not appear to be ordinary at all. A second explanation followed. If the missing mass is not ordinary, perhaps it is a different kind of matter. Particles that interact through gravity, but not through light. Such matter would have mass, would shape gravitational wells, would influence the gas temperature exactly as observed, and would remain invisible to every telescope ever built. It would explain the cluster measurements perfectly. This idea is internally consistent, the numbers work, the gas temperatures fall into place. Cluster structures, simulated under the assumption that this kind of matter exists, look like the real clusters astronomers observe. The problem is that this explanation requires the existence of a particle that has never been directly detected. Decades of dedicated experiments, underground detectors, particle colliders, sensitive recoil chambers, have been built to find it. None of them have. The candidate explanation works on paper. The candidate particle does not appear in the laboratory. A third explanation goes deeper. If no new particle exists, perhaps the equations themselves are slightly wrong. Gravity as currently formulated may behave differently at the enormous scales of galaxy clusters than it does in the solar system where it was first tested. A small modification to the law of gravity at low accelerations could, in principle, produce the observed temperatures without any missing mass at all. Modified gravity is not a fringe idea. It has been developed seriously, refined for decades, and shown to explain certain galaxy-scale observations remarkably well. But at the cluster scale, the same modifications struggle. The temperature mismatch in clusters is too large for the proposed adjustments to fully absorb. Some residual missing mass remains even after the equations are bent. The bend helps, it does not close the gap. Modified gravity cannot eliminate the shortfall, it only reduces it. A fourth approach attempts a hybrid, partial modification of gravity combined with some quantity of unseen matter. Each piece does some of the work. Each piece compensates for what the other cannot do. Hybrid models can fit the cluster data, but only by introducing two unknowns to solve one problem. The explanatory cost rises faster than the explanation closes. None of these paths reaches a clean resolution. A fifth direction questions the measurement itself, not the instruments, but the assumption underneath them. The gas temperature calculation assumes the cluster is in equilibrium, that the gas has settled, that the gravitational well is stable, that motion has reached a steady state. If a cluster is still being assembled, still absorbing infalling material, still ringing from recent mergers, the gas could be hotter than its equilibrium value. The mass would not be missing, the clock would simply be off. This explanation works for some clusters. Some are clearly disturbed. Some show signs of recent collisions, but the shortfall is not limited to disturbed clusters. It appears in the most relaxed, oldest, most settled systems too. Clusters whose gas should have reached equilibrium billions of years ago. The non-equilibrium explanation removes a fraction of the discrepancy. The core of the gap remains. 5 candidate explanations have been examined. Each one has structure. Each one has predictive power. Each one fails at a different point. The gas is too hot in too many clusters, by too much, for any single resolution to absorb. What remains is a measurement that holds steady across every observation and an explanation that does not. The deeper problem is not the size of the shortfall. It is that the shortfall behaves consistently. If the missing mass were a random error, it would scatter, sometimes too much, sometimes too little, sometimes in the wrong direction. Instead, the gas temperature in clusters scales with the visible mass in a regular, predictable way. Whatever is missing follows a pattern. It is distributed, it is structured. It responds to the same gravitational dynamics as everything else in the cluster. It is not noise. The missing mass behaves like real mass that no instrument can see. This is the boundary where the evidence stops being able to guide the theory. Every measurement that could constrain the unseen component has been made. Every laboratory designed to detect a new particle has been run. Every modification to gravity has been tested against the data. The result is a stable, repeatable, multi-decade observation surrounded by candidate explanations that each fail at different scales. The cluster does not care which explanation is correct. The gas continues to glow at the wrong temperature. There is one partial answer that survives the scrutiny: that the universe contains a form of matter that gravitates but does not radiate, and that the missing mass in clusters is the same component that shapes galaxies, structures the cosmic web, and bends light around distant objects. The internal consistency of this framework is unusually strong. The same unseen mass, postulated independently from 5 separate lines of evidence, lands at roughly the same total amount in every case. The framework holds together. The substance does not appear. This is the layer that has been resolved. Whatever the missing mass is, it behaves like a real gravitating component of the universe, present in every galaxy cluster ever measured, scaling cleanly with structure, leaving consistent fingerprints across independent observations. The shape of the answer is known. The composition of the answer is not. The cluster gas keeps its temperature. The mass budget keeps its shortfall. The detectors keep their silence. What can be confirmed about galaxy clusters is that they are heavier than they look, by a margin that has not narrowed in 50 years of effort. What cannot be confirmed is what carries the extra weight. The matter, if it is matter, has been weighed many times and seen exactly zero. The clusters continue to do what they should not be able to do. Something inside them is heavy, structured, and invisible, and the universe has not yet given up the name of what it is.